As I mentioned before, this is like a very knowledgeable crowd. So feel free to pitch in and share your ideas. So today we're going to be talking about PyTorch and handwritten digits. But more generally, we're going to talk about image processing using AI or neural networks using the Star cluster. So I want to begin by having some acknowledgements. So there are 3 different grants that are involved in today's talk. One is an NIH grant that funds my work, also the instrumentation grant that funds the cluster, and also Pulse grant that is facilitating the lunch and learn. So we're lucky to have a lot of support for this activity. I just want to thank the 2 organizers of the lunch and learns, which are Dr. Paul Yang and Dr. Ed Curry. And Michael basically got my programs to work on the cluster 2 days ago. So I'm very thankful of that. I also want to give acknowledgement to my students at Hofstra who are, I'm going to highlight some of their work that involves neural networks and images. And like most people who work in radiology, it's an interdisciplinary team. So here at Hofstra, we have 4 students. The work that I'm going to be highlighting today is Sandro and Justin. They worked on neural networks. But Allison and Quinn work in biostatistical analysis of data. So, this is like a combination of projects. I have collaborators in radiology departments, psychology departments, and electrical engineering departments. So this, luckily, this is supported by our grant, which creates access for the Hofstra students to communicate with our collaborators. Why am I here? There was this cluster, and then there were people who were hired as part of this cluster. So Gustavo, Kate, Paul, and I are, trying, sort of to promote AI here. And, anyway, so I feel excited to have a cohort of faculty that are helping us navigate, this experience. So, I'm going to be talking about recognizing digits, but first I want to say why I care about image processing using neural networks. And for me, it starts with magnetic resonance imaging. So it is a very versatile technique, but it's slow. So the work that I do tends to focus on accelerating MRI, maintaining image quality. This is actually a picture of me as a postdoc at Stanford. When when you're a postdoc, you're the guinea pig of the study and you analyze the data. So I have a lot of scans. My knees and spine are in like lots of publications that my other colleagues were doing, and they needed a body in the scanner. For Christina, who works in the Fourier domain, this is like a very familiar image, but I just want to say for the students who ever said, why is it that we need to learn imaginary numbers? They're not even real. It turns out that the data from an MRI scan, it's complex, which is a real part and an imaginary part. So to process data from an MRI scanner, you process it using the real and imaginary components of the image. Now, the equations look a little like ugly, but they're actually just like projections into sines and cosines. And the Fourier transform is the data acquired in the MRI. And in imaging or in inverse problems in general, you have that data and you want to reconstruct the original object for the simplified version of an MRI scan. Just doing the inverse Fourier transform gives you the kind of image that you might be used to seeing. So underlying what we're going to be doing is MRI data, even though this talk is not really about this. What it is a little bit about is about how to interface neural networks with images. So if you want to go faster in an MRI scan, what you do is you collect less data. The slow component of the process is the data acquisition part. So this is a sampling mask. So the white areas are data that is collected. The black areas are data that is not collected. So what you have in the center is a fully sampled image where I'm going to see if I can dim the lights a little bit. But we have the don't go to sleep. So we have the fully sampled image. This is what a brain would look like if you had collected all of the data. The undersampled image is where you only collected the data that is in white. So you see it's like slightly randomly sampled with a central region that is fully sampled. But what you end up seeing here are these artifacts. So there's like these vertical streaks that appear in the image because you didn't collect all of the data in this direction. right? So when you accelerate the collect less data, there's a price. What neural networks are trying to do is they're trying to reduce the effect of that. Now, people here, speaking to this crowd, I don't necessarily, hi Chris, it's not necessarily something that I need to explain too much, but it's kind of interesting because AI is like a big thing right now, but it's the old thing. So artificial intelligence in its broadest sense, it's significantly old, and a subset of that is machine learning, and a even smaller subset of that is deep learning. What we're going to be doing for, handwritten digit recognition is not deep in the sense of deep learning, but it will be using neural networks like deep learning is. So this schematic is just an example of one of the many architectures that people use when they're trying to use neural networks for imaging. It's called a U-net, and it has certain properties, but it's called a U-net because it looks like a U. So, but in particular, it's a way of an image is a matrix of pixels. And what you do is when the image is presented in a camera or presented on the screen, it's represented by pixels. But what the neural network does is it takes that pixel representation and it changes it to a different feature domain. And in this feature domain, this usually lower spatial dimension domain, you hope to keep the fundamental components of the image and lose the noise, lose the things that you don't need about. And this is one of the ways in which you hope that you're going to speed up the process. One of the huge differences about neural networks than things that we did before is that before, if we wanted to detect something, we would try to say, okay, if we want to see a tumor, I need to get like the edges of the tumor, so I would have an edge filter. Or maybe I would want to see like the texture of the image, so I would have a texture filter. The nice thing about neural networks is that it comes up with its own features itself. And that's like a fundamental difference. So they're not human developed features. The process of classifying and identifying the features are all in together. So that's neural networks. I'm going to say, very quickly, like what it is that I do. I'm not a neural networks expert. Actually, I'm not an expert on many things. I'm a jack of all trades. But what we do is we try to say, I don't care if your image looks nice. I just want to see if you can detect a tumor. So we're going to do a very, very simple experiment here. This signal is in the middle of either this image or the image here. So this is the image to your left. This is the image to your right. A two-alternative fourth choice experiment. The person doing the experiment needs to say whether the image is into the left or to the right. So we're going to do this here right now. And this is fourth choice because if you don't know, you just guess. You can't say, I don't know. Raise your hand if you think that the little center dot is in the center of the image to the left. I have a few. Raise your hand if you think it's to the image to the right. We have a few less. So it turns out that the signals are designed to be difficult to see because you want to be able to judge subtle differences in the image quality. So in this particular case, it is in the center of the image to the left, but it's designed to be hard to do. So the better imaging system is the one where you can see tumors better. It's not the one where the images look pretty. Now, more related to neural networks can generate images. And in this particular case, we have a brain, we have a region of the brain. And in this region of the brain is being reconstructed with networks that keep getting, faster, faster, faster. 5x networks is five times as fast as the original. It also means it collects 1/5 of the data. So 4/5 of the data is not collected. That data is being filled in by a neural network. So you see that the difference between the original image and this image, there's some like weird structures that start to appear that are not in the original image. So these are image artifacts that are basically brought in by the neural network that put them in the space where you didn't collect data. So if we put in a signal, that makes it a little, very interesting because we have a signal here and no signal here. As we accelerate, we see, okay, we can see the signal, we can kind of see the signal, maybe we don't see it, maybe we don't see it. And then there's something actually that kind of looks bright here. But the catch is that this thing that also seems to show the signal also have these anatomical structures that are not present in the original image. So the fear is that the neural network is creating plausible images, artifacts that look like anatomy, but it's not real, right? So this is the same thing happens with your large language model when your neural network makes up references to your paper. It's actually creating anatomy that doesn't actually exist. So I just want to say, I'm saying, I'm a worrywart. I worry about the errors of neural networks, but the images look kind of impressive. So here is an image of an accelerated reconstruction that was not processed by a neural network. It's a standard MRI reconstruction method. This is the original image, and this is the image reconstructed by a neural network that introduces physics into the model. And it looks pretty impressive. So the kind of stuff that we do is evaluate image quality, not by SNR, not by there's SSIM, other metrics of image quality. We do it by tumor detection. And the places where the students here at Hofstra have been working on is, I showed you this two alternative force choice task. A force localization task is a little bit more advanced. So here we have a region, and the person needs to find the tumor somewhere in that region. So they need to localize the lesion. So this is work from students here at Hofstra. So when they train, you can see that the green circle is the true location. The red circle is the guess from the neural network. And in the training image, in this case, it got it right. And here we have a testing image, and we see that it's close, but not quite right. So we're developing neural networks that kind of try to find lesions in tumors. Now, that was like, why do I care about image classification? But what you actually came here today is because you actually want to do it yourself. And one of the classic problems is the MNIST dataset. So this is the National Institute of Standards and Technology, and it's modified. That's the M in the MNIST. And it's modified because the original version had different image qualities, different sizes, and a set of computer scientists decided we need to have a standard test for machine learning. And when this, so you can see, in this case, it's the output of actually the neural network that you're going to be training. And this 5 looks a little bit like an S. This 3 kind of looks like a 3. In this case, every ground truth, in this case, this is an example of an error, right? Because the ground truth is a 7 and the prediction is a 3. So this algorithm is not always perfect, but in most of these,
the 7 with the line in the middle.
If you're looking at the mail, people, my dad is a doctor. He's got a horrendous handwriting. So like the ways in which you can mess up digits, it's pretty impressive. Huh. And neural networks make mistakes. So this used to be like a very difficult task that became kind of like easy in the time of convolutional neural networks. So what we're going to be doing today is we're going to be using the GPU cluster to train a super simple neural network to classify handwritten digits. And you can see, for example, that one is like, it's almost impossible to get right? So if I were to look at it visually and I didn't know what the ground truth was, 7 or 3 could be 7, but could be 3. The 1 is pretty clear. So, and this used to be a very hard thing to do. Right, so this is a little bit of what I said in words. The original NIST images, varied, in size, image quality, and then there was some standardization of making them all 28 by 28 pixels, and this became a benchmark that you're going to see how, with a very simple neural network, we're going to do amazingly well. So the neural network that we're going to be looking at, we're going to look at it in slightly different ways. But this is like a very, very, very simple neural network. So you have an input. Now, this is a convolutional neural network. And basically, a convolutional neural network is like you have basically a filter, and you move it all around the image. So in this case, you might have 32 filters that you move around the image. So each filter has an output for every location. So the input is one image that is 28 by 28, but the output is going to be 32 filters by 28 by 28. And then you filter it. So in this filtering operation, there is a ReLU, which is a nonlinear operation. So the neural network has filters and nonlinearity, right? So you have a second layer, And after you go through 2 of these filtering and nonlinear operations, what you do is you do a max pooling. And a max pooling, it basically says, my images are too big now. I'm going to reduce their size by taking a 2x2 region and taking that maximum value of that. So you do that twice, and you end up getting with something that has 64 by 7 by 7, right? So now that is basically a 64 filters in a very coarse spatial discretization. Dropout is an interesting thing. When you train a neural network, you update the weights on the different layers, but if you do it too well, you end up overtraining on your training set. So basically, you get too good at the training data and you don't generalize well. So this neural network has a simple dropout, but that means that when it trains, it only trains 75% of your data each time. At the end, you end up with something that is not a convolutional neural network. It's just a regular connection between basically arrays. So we're not going to go into the details of a neural network, but to give you an idea, this is how many layers? 1, 2, 3, 4. Dropout is not a layer. 5. I guess 6 layers. It's very small. Like the neural networks that were typically used for this kind of thing might have 48 layers. They might have hundreds of layers. So where does AI come? So AI already came in the generation of the images, in the modeling of the humans detecting tumors. The PyTorch notebook that I'm going to show you was generated by ChatGPT. So what I did is, I used to use TensorFlow, which is a different framework for neural networks, but this was like PyTorch versus MNIST. So I had to go and do something in PyTorch. So my students know PyTorch better than me. So I just put it in on ChatGPT, and I got something that I could modify, right? So the catch there is that it accelerates the coding for somebody who knows how to modify it when they need to. It's risky if you just take the output as it is. But the Jupyter notebook that I'm going to show you is something that was generated by the Hofstra ChatGPT. So I think, you've been very patient. You've heard me talk. So now it's time for us to actually run. Before we go for it, does anybody have any questions at this point? Now in this page. So raise your hand if you are in this page right now. Anybody not in this page? Awesome. Right. So what we're going to do is from here, we're going to go to Jupyter Lab. Right. And in Jupyter Lab, you're going to have some choices. So we're going to be using a GPU today. So the queue, we're going to do a normal queue. That should say the same. I think I already changed this when I first logged in, because I think it starts off with a CPU. Then there's an A30, but it turns out that our cluster has more of the fancy GPUs than on the really cheap GPUs. So we're going to use an A100. So I'm going to wait until, yeah.
Oh, no, that wasn't a question.
Yeah, I was going to say, please correct me because, like I said, I don't know very much. So I chose just 1 core and 1 GPU and 1 hour, right? Because what we're going to be doing is really simple. And then you launch your session. And now we wait, right? So it'll take a second before, the session is started. And now this button that says connect to Jupyter should come up. I'll give it a second or two. Okay, I'm getting, raise your hand if you don't have the Jupyter button. Yeah.
Oh, you can press because it's the first one. Take it normal.
Oh, great. Yeah, awesome. Great. So just to be sure, raise your hand if you have this visible right now. Great. We're all to, yeah. Well, if you're shy, then I pick on you even more. So, okay, so now we're going to connect to a Jupyter Notebook. So if you were here at Paul's Lunch and Learn, you saw Jupyter Notebooks, but this is like a come whenever you can situation. So this might be the first time that you have been using a Jupyter Notebook. And for those of you who haven't used them before, they're very, very nice. So this is going to begin with so when you logged in, you probably didn't get this, right? Because I have come here before. So in my case, I think I'm going to try to reproduce it. So in your folder, maybe you got something like this. Awesome, thank you, Christina. So there is a link. So I want you to, I think actually now I don't know which one it is, whether it's, I think I'm gonna find out soon.
Yesterday. It was full.
It was a full November, right? So I'll come here. So when you're here, I have multiple versions of November 5. Right, so I want you to go to the November 5 folder. I think we're all here, right? So now what happens is that there is an environment there, and I think Paul talked about this. In order for this notebook to run, it needs to have access to a bunch of packages, and we could load them every time, or we could create a virtual environment that has those packages preloaded. And with Michael's help, I hope that these are accessible to you when you get to the notebook directly, which makes things a lot nicer. So, so there should be, and then there is so you should have a file there that says MNIST PyTorch classifier final. Okay, I'm seeing it. Yeah, so just double click on that, and that should bring you to this file. Raise your hand if you are here. Great. So now the other, I'm going to actually maybe minimize this because my own camera makes it. So there is, I just want to make sure that you have the MNIST environment. So in the top right, I want you to see there and see if you can find the different kernels. I think default might be Python 3, but I'm not sure if MNIST was preloaded as a default for you. It was? It was perfect.
Nice.
Great. Thank you, Michael. So so this is an environment that Michael and I put together a couple of days ago, just so to have the packages that we need for this notebook. And basically it's the neural networks for imaging packages that you would need. So what this notebook is going to do, so everybody so now everybody is going to be running on a GPU, which is going to be about 10 times faster than if you did it in a CPU. And you also have the packages pre-installed, which basically that's what you do. You create a virtual environment, and I actually never change it. So it's been so long, it's something, because once that you create it, you keep using the same thing. So we're going to download the MNIST data. We're going to build a small CNN. We're going to train it and show some sample solutions. So you can run the whole Jupyter Notebook at a time, but I like to run it cell by cell. So the first cell, let's see what it's doing. Right, so here I'm importing the packages that we need for this. So I know that Paul used sklearn. That's a very common machine learning package, and I think he did it for time series. But in our case, we're not doing we're not doing time series, we're doing neural networks for imaging. Yep. So we're going to be using Torch Vision. Mm-hmm. Right, and Torch Vision has things like data sets and transforms. And the MNIST data set is such a benchmark that it's built into Torch Vision. So I don't even need to go get it anywhere. It comes with the package itself. And the transforms, it's basically pre-processing that you do for your images. And there's like lots of things that you can do, like crop your images, rotate your images. We're going to do something super simple in this case. We're just going to normalize. But you can see that there are, there's some fancy widget kind of things that it shows you a bar. That's the TKDM. So like I said, so this was generated by ChatGPT. The thing that's, so it saves me a lot of time. But if I didn't know what those things were originally, then if something broke, I wouldn't know how to change them. So that's like a speed of of the coding, but just beware. So this is fixing the seed. So here we're going to be randomly sample data for training and testing, and if you don't set the seed, every time that you run it, you get like a different training and testing set. So and there's a lot of variability sometimes between training and testing sets. So if you don't, it's a pseudo-random generator, and this allows you to debug with the same training and testing set. By the way, I'm talking too much and not listening enough. So if anybody has any questions or comments about anything that I say, please don't. So what happens here is, right, so we import the data set.
Question.
Yes.
Okay. I've always wondered does it matter what you set the seed to? Like, what is the number associated with the seed mean?
Yeah.
You can do multiple?
That's a great question. So these random number generators do something like take that number, multiply it by a humongous prime, divide by other horrible number, take the remainder. That's pseudo-random, right? So that seed is like the initial multiplier of that like very large prime. And if you pick a different one, then the sequence is different. So it doesn't matter actually which one you pick. It just matters that it's the same each time.
Yeah, I was going to say, but if you pick the same one, you get exactly the same sequence of numbers. Even though it looks random, it's all exactly the same, reproducible.
Yeah. Thank you, Bob.
So I always thought of like basically you have a list of random numbers, and then basically that tells you the address where you want to start, because every time you sample a random number, you're going to hop to the next one. Is that?
I'm not an expert on pseudo-random number generators. My simplistic view of like remainders of very large things is like,
you get a random number, but then the next one might be 43, and then give you another random number.
But it's the same sequence if you start with the same one. Yeah.
Meaning, if we sample 1,000 random numbers here, it's going to look like the same 1,000.
Exactly the same 1,000. That's right.
Yeah.
Great question, Kate. And if anybody has any more questions, please. We get a room full of experts. So it's interesting here too. I always think that this is pretty cool. CUDA is the language of GPUs, and if it doesn't have a GPU, it goes to CPU, right? So it's going to tell me that I'm going to using the device that is CUDA is basically a GPU, and I remember. So here's a little bit of a story. My old PhD advisor was one of the early adopters of neural networks, and we would go. Students from his lab would go to when the PS stations were first sold and get a lot of gaming systems, and then extract the GPUs of the gaming systems to run image reconstruction experiments. But programming at that time on a GPU was horrendous. So then now they made it a lot easier, so much so that we can do it here. So that was that cell. Now here, and you can see, so this was generated by ChatGPT. But it comments it so that it's somewhat reasonable. I added some of my own comments when it wasn't so clear, but it turns out that there's a couple things that might be helpful to know about a neural network. One of them is epochs. So the way that a neural network is trained is that you have your training data, and you go through your training data multiple times, and it's not a completely deterministic learning. So you have to go through your data multiple times in order to minimize, to get the best weights. A batch size is the number of, in my case, images that you're loading each time to the GPU. So if you have a very large GPU, you can have a larger batch size because it uses more memory. I have an old computer with a small GPU. My batch size is 1 because I don't have that much memory. So if you have a small GPU, you can still do interesting work, but you might just need a smaller batch size. And then there's other components in terms of learning rate. There is a new neural network class coming to Hofstra. I don't know when it's going to run for the first time. Does somebody know by any chance? But it was part of the data science program, and that's going to be exciting. But at this point, the transform is something very simple. But what it does, it basically takes the data, which is loaded into Python, and it needs to convert it into a tensor so that it runs on the GPU. So there's things that run on the CPU, And then there's things that run in the GPU. So it takes the images and converts them to tensors. And then I normalize them because, generally these algorithms work better if the data itself is scaled appropriately. Yeah.
Why normalize to these horrible numbers and not 0 and 1?
Yeah, so that's a great question, Paul. And it's a great question because I didn't know the answer to that either. So I went and I looked at what those numbers were. And it's the mean and the standard deviation of the MNIST dataset grayscale values themselves. So it's doing a standardization, not a normalization. So you could have also had them go to 0 to 1, but what ChatGPT chose to do was use a standardization as opposed to a normalization. To be frank, generally I use 0 to 1. So and then now we're not here. So basically what we're going to do now is we're going to get the data. So let's do that cell. And here basically we're going to have a training set and a testing set. So we're going to have some data that we're going to use to train a neural network and some data that we're going to use to evaluate it. And these data loaders are like basically telling Python like how many images to get, how to load them into the training cycle. Now we're going to have a small neural network. And neural networks look fancy, but this is everything that defines the neural network. It's not a deep neural network, it's a small neural network. And here you can see that the first layer is a convolution layer that comes to the second layer is another convolution. So this is like the code equivalent of that picture that you saw in the presentation. And the picture that you saw in the presentation was generated by me giving a ChatGPT the output of this code and saying, create a picture for me of that neural network.
Oh, really?
Wow. Yeah. So it's nice. And actually created 2 pictures. I'll show you the other one in a second. The one that I showed you first was an image. It also created an ASCII. So this is the same architecture that I showed you before. And this is the basically the text version of the small neural network that does the same. So I also asked it to create a schematic of the model, which is kind of like the same thing, but it's a little bit easier to read than the text, right? Because your input image is 1 by 28 by 28. Of the first layer, the output is 32 by 28 by 28 because there's 32 filters that get moved all around this image. And for each filter, you have a 32 to 32. So it looks weird that you end up with a much higher dimensional thing than the thing that you started, but you end up at the same, right? And then it shows you this nonlinear activation function. So neural networks are not linear, right? Which makes them hard to interpret. So this is just a picture of the same thing that you've seen before. And like I said, that was ChatGPT generated. And then you look at it and it makes sense. And at the very end, after you go through this, the output of this neural network is it's 10 numbers. And for each number, it gives you the probability that it's that digit. So the outputs of the MNIST is going to be 0 to 9. So the output of this neural network is going to be probability of 0 is 0.07, but the maximum probability of those 10 numbers is what the neural network will assign to that particular image. Right, so, and that actually, that's a cell that doesn't do anything. So, and now this cell, right, is defining the loss function. So you have a neural network. So we're talking about, it has to minimize something, right? And for a classification task, it minimizes the cross entropy. That's a fancy way of saying, like, if you do logistic regression, it's the binary cross entropy. And if you do, 10 class classification is the cross entropy loss. And the atom optimizer is a fancy way of like trying to minimize a very high dimensional object, right? So if you think of like the number of weights in this neural network, actually for this one might not be too bad, but for like the other ones are like millions and millions of weights. And people spend a lot of time in terms of figuring out how to minimize functions in very high dimensional spaces. And one of those is called the atom approach. Right, so and then, okay, so now we're gonna do, so we create some functions here that are gonna help us with the method. So basically one of the functions is we're gonna train on one epoch. And it essentially goes through the data, taking the batches, and then up. So usually when I teach Calc 3, I always say that it's my favorite application of gradients, because the minimization here is something related to stochastic gradient descent. So basically, and it's not stochastic in the way that you think. It's not like completely random. It's just like, because you only take subsets of the data, it's not computing real gradients. It's only computing partial gradients. So you end up doing a minimization, and it keeps track of the loss, right? So this is like training one epoch, and then this is for evaluating. This is, yes.
Well, just, I'm trying to keep up with the terms here.
Mhm.
So the epoch is you taking a subset of the data and doing one step?
Yeah, great. Thank you, Gustavo, for that question. I choose my training set size.
Right.
So I think I picked like 1,000 or something for this. 1,000.
But you said a subset, so you're gonna compute a gradient based on that subset of the data, so it's not a gradient based on the total data.
Right.
So it's not a complete gradient.
Yeah, so I'm going to repeat what Gustavo said, but I'll clarify a little bit. So imagine that my training set is like 1,000 images.
Yeah.
My batch size is 10 images. So if I was doing my a batch size of 1,000, then the gradient would be the gradient, because I took the whole thing. But because I have a smaller batch size, I compute the gradients on just my batches, and instead of a true gradient. And that's actually the stochastic part of it.
And do you do the?
And one epoch is the 1,000 images. It's like the whole training set.
So do you eventually do the pseudo gradient for the full?
Multiple
sample,
times.
But in different batches?
You do the same process multiple times.
Yeah,
Right.
but you never calculate the full gradient, because
Right,
that's
right,
too, you can't fit.
Yeah. I
Now,
understand.
are the batches different from epoch to epoch? Is that what you mean?
Yeah, if you have 1,000 images and you decide to have batches of 100, is it gonna be, they're not gonna overlap, or are you gonna sample run them?
Oh, no. They don't overlap. No.
They are divided equally in 10 parts, and then
Yeah.
you do a batch, 10 batches, 10 gradients.
And each time you move in the direction of your little
gradient.
gradient.
Done, that's an epoch.
That's an epoch.
I've done.
Yeah, one epoch is one pass. through the day.
Is that better than if you could do one epoch with one batch? Would that be better? Is that something you have an answer for?
I think heuristically, yes, it's better to not do the whole thing.
Yeah.
And it's because of local minima and high dimensional spaces.
Right.
So this is a little bit beyond the
know.
intro to, but the underlying really interesting question is that if you were to look at the thing that you're trying to minimize, is got like millions of local minima. And what a full gradient would do, it makes you more liable to get stuck in a local minima, whereas the lots of little gradients makes you less likely to get stuck.
Right. That makes sense.
Yeah. Which, I think that they discovered in this process. It wasn't obvious.
Yeah.
Usually, you would want, here's another thing that is interesting. People usually want to use as big of a batch as they can that their GPU will hold, right? Because the limiting factor is how many images can you have in your GPU? It turns out that if you look at performance, when I talk to the medical imaging people, they like small batches because of the local minima problem. So even though they have bigger GPUs, they use small batches. So this is a function of you train and you evaluate, right? You evaluate different data than you train. And then, so now it gets exciting. We're going to see this something a little bit. So you're going to see, so when you run this, so I think Paul ran this on a CPU.
I'm getting 4 iterations per second.
Right.
70 iterations per second?
Yeah. So, I mean, I almost wish that we would do half the class. So now, so this is a widget. So this is one of the things that we did at the beginning that shows you the progress of the training. We're going to go back and look at the code, but you can run it again if you want to see it. But I actually also did this on a CPU before I did it on the GPU, and I got tired of waiting. So the difference in computation time is kind of amazing. And what you see here, you can see the epoch happening as the batches get moving. Maybe I'll do this again. Actually, maybe I'll look at the code and you can. So what is this? So now this is actually pretty simple, right? So what is going, I only did 2 epochs. And then it goes through the epochs. and then it basically it evaluates the training and testing, and then it basically appends the training loss and training accuracy, to a file, and then it prints it out. So what is basically, so let me do this again. Right. So as it's almost too fast. And something else that I want you to sort of see that is kind of ridiculous already. When you see the test accuracy of a single pass through the data is 99%. So this used to be like a very difficult machine learning task, right? Before convolutional neural networks, people were trying all kinds of things to be able to do image processing. But this neural network architecture made this task really easy. That, with a small neural network, we can get behavior that's pretty fast. The training, testing, that's like in the machine learning class, you would see that. It's always, one of the things that I like about images is that we can see them. So let's see what we're doing here. We're going to show prediction. So basically, in this case, we're going to have the ground truth, and we're going to see what our models predict, and then we're going to see if the ground truth matches the prediction of our model. And here we have that previous case that we have seen before where it gets it wrong, but in I think every other case, the neural network got it right. So it could tell that this is a 5, this is a 5. Remember, there's only 0 to 9. But a car, self-driving car, is doing the same thing, right? It's scoping its environment and doing classifications of thousands of objects. This is a classification of just like 9 objects. For the students who are younger, you might be too young to be amazed by this, because I have been working in images for a long time, and this looks horrendously hard to me. And the fact that in like 15 minutes using ChatGPT, we can generate something that classifies handwritten digits, that kind of blows my mind. But then again, I didn't grow up with ChatGPT on my phone. Cool. I did. Raise your hand if this worked for you. Great. This is really great. So I think that's all I got. Oh, Gustavo.
I keep dragging this.
No. Please ask.
But like, there's so many weights to this, right? How did you have at some point there? Do you choose initial weights?
That's a great question. So I'll give you 2 answers. For the work that we do, which is like with MRI images, and the networks that we're doing there are way bigger. We have done it by initializing the weights based on natural images, where Google will use millions of images to train those neural networks and hours of many GPU times. And then what we do is we fine-tune the weight that Google generated. So that's transfer learning. What that does is it makes it so that with a few images, I can just fine-tune my neural network to my medical images. Right. So that we do. We also sometimes train from scratch, where the initial weights are random. And the difference we get, actually, in my application, we get to about the same place. It's just how long it takes to get there. So the number of epochs that I need to go from random weights to good performance is more if I start with random weights than with like the trained on similar images kind of weights. Yeah, and there's different ways to initialize. I didn't actually check the way that they were initialized here, but the problem is simple enough that I think it wouldn't change that much.
That's interesting. So if you have a neural network, so about this transfer that you said, but what if your neural network is different, the depth?
Yeah, if you change the architecture, you can't move the weight.
You can't. It has to be the same.
At least I do not know how to. Sometimes what we will do is we will take a neural network and add layers that are, imagine that you want to keep the weights, and then you freeze those, and then, which we are currently doing, and then we have like a little neural network at the end. So I can change it by adding something at the end, like a post-processing step to the output of a neural network, something along those lines. Out of curiosity, raise your hand if you had trained a neural network before today. this is amazing. This makes me feel so good. Because now you see that it's really accessible and it's really powerful. Great.
Thank you, Anton.
Yeah, thank you.
There are other questions that are here online? Nobody's online.
Perfect.
Questions. Early on in the presentation, we were talking about the very first slide you showed, where you were saying that some of the data was missing.
Mm-hmm.
What gives rise to the data that's not there?
Yeah, that's a good question. Most of the time when we're looking at missing data, it's something that we don't want, right? It's like there was a corrupt device or we didn't collect that data. In an MRI scanner, you basically there's gradients that collect the data for the Fourier domain, and there's one direction that is very fast. So if you look at this direction, it's always full, but then you have to like move a gradient, and that's very slow in like a mechanical motion of a gradient that's very slow. So and that's this direction. So the data that is missing is a MRI scientist saying, I want to go faster. And I want to go faster by collecting less data because then my patient leaves the scanner faster. But I want to do it in a non-structured way. Because if you did it regularly, the missing data would have like very clear structure that would make your images lousy. But they do it pseudo-randomly. And that way the generated images with this. So this doesn't look too bad. If you had collected every other image, it would have like 5 versions of this brain overlapped on it. That would be horrendous. So the missing data is the attempt at having you be less time on the scanner, but it's deliberate. Yeah.
Thank you.
Yeah, great question.
You did a really nice job of the presentation. Very impressive.
Thank you. You guys are a fantastic audience, and I'm so excited that we train I have several students in my classes now, and some of them I think we might have to do some training of neural networks there. So yeah, thanks. And then the next talk we have Michael. So actually maybe I'll do the promo for the very next one. So let's move, because I am like a beginner really. I am actually looking forward to seeing Michael's talk on working with GPUs. So
Yeah, looking forward to it.
thank you.